We continue our study of logic by now looking at multiple quantifiers. So let's imagine that we are visiting a factory that manufactures computer microchips. The factory guide tells you there is a person supervising every detail of the production process. Which of them best describes the meaning? There is one single person who supervises all the details of the production process, or for any particular production detail, there's a person who supervises that detail, but there might be different supervisors for different details. Well, in fact, either of these interpretations could be what the guide means. By itself, that statement is truly ambiguous. However, it is possible that something else the guide said may clarify this ambiguity by giving the statement context. We often encounter ambiguity in our ordinary lives. Sometimes context is given. Other times, we just simply misunderstand each other. In mathematics, however, it is important that everyone interprets the statement the exact same way. For this reason, a convention has been developed. When a statement contains more than one kind of quantifier, we imagine the action suggested by the quantifiers as being performed in the order in which the quantifier occurs. So consider the statement: for all x and d, there exists a y and e, such p of xy. In order to show that this statement is true, we must meet the following challenge. Imagine that someone is allowed to choose an element whatsoever from D. And imagine that person gives you that element. Call it X. Your challenge is to find an element in E, call it Y, so that the person's X and your Y taken together satisfy the property P of XY. In other words, someone chooses an X and you must find a Y that satisfies P of XY. So it's a game. So let's examine this using a Tarski's world. So we want to show that this following statement is true. For every triangle X, there is a square Y such that X and Y have the same color. So the goal, remember, is that someone chooses a triangle X. And it is our job to find a corresponding square that has the same color. Well, let's create a table. X, color of X, and then a Y that we can choose. All right, so we need to find triangles. Okay, well, the first triangle I see is D. So let's say that someone chooses triangle D. Well, the color of that is black. So our goal is to choose a black square. Well, E is black, and it's a square, so choose E. Okay, let's suppose that someone gives us triangle F. Well, that's gray. So we now need to find a gray square. Well, we have two choices. We have G or H. I'm just going to pick G. Last triangle, let's suppose that someone chooses triangle I. That is also gray. So by the way, our previous choice would still work. We can choose square G. Well, those are the only three triangles that appear in this Tarski's world. So we have just shown that given any triangle that could possibly be chosen in this world, we can find a square that has the same color. And so this is indeed a true statement. Same Tarski's world, but now we're going to look at the statement. There is a triangle X such that for every circle Y, X is to the right of Y. Okay? So we have X, column that X is in, Y, and then column that Y is in. So here what we have to do is we have to find a triangle that is to the right of any circle. All right, well, we have D, we have F, D, and I. Well, if we choose F, for instance, the column that F is in is the third column. Well, now we have to look at every possible circle, and there are three of them. There's B, C, and A. Well, B is in column 1, C is in column 2, A is in column 3. This means that F is not to the right of A. In order for it to be the right of, it has to be in a larger column. So F does not work. I actually didn't need to erase that Y column. Okay, well, D or I. Let's look at D. That is in column 4. And again, we have three circles B, C, A, and we already said column 1, 2, and 3 respectively. Well, look, there's a triangle that's to the right of every circle. And so this is a true statement. So here's how we would interpret statements with multiple quantifiers. So if we have the statement of the form for all x and d, there exists a y and e such that p of xy, allow some to pick whatever element x and d they wish, then you must find an element y and e that works for that particular x, like we did in this example. To interpret a statement, there exists an x and d such that for all y and e, p of xy, you must choose an element x and d such that someone else cannot choose an element y in E that fails to work with your chosen x, like we did here. We chose the triangle D such that they could not find a circle that was not to the left of it. So we made it impossible for them to win the game. Let's look at a more detailed example. So a college cafeteria line has 4 stations: salads, main courses, desserts, and beverages. The salad station offers a choice of green salad or fruit salad. The main course station offers spaghetti or fish. The dessert station offers pie or cake. And the beverage station offers milk, soda, or coffee. 3 students, Uta, Tim, and Ewan, go through the line and make the following choices. Uta chooses a green salad, spaghetti, pie, and milk. Tim chooses a fruit salad, fish, pie, cake, milk, and coffee. Ewan chooses spaghetti, fish, pie, and soda. We now wish to determine the truth value of these 4 statements. So we'll look at these one at a time. The first statement: there exists an item I such that for all student S, S chose I. Well, let's first rewrite this. So that first statement said, there is an item that every student chose. Well, we look. And we go, oh, look, right here. Pi, pi, pi. This is true. They all chose pi. The second statement, there exists a student S such that for all item I, S chose I. So if we rewrite this, what this is saying, there is a student who chose every item. Well, there's green salad, fruit salad, spaghetti, fish, pie, cake, milk, soda, coffee. That's a total of what? 9? Green salad, fruit salad is 2. Main course station is spaghetti and fish. That's 4. Pie, cake makes 6. And then 3 beverages makes 9. So is there a student that chose all 9 items? Well, Uda had 4. Tim has 6. Ewan has 4. No, there's no student that chose all 9. So this statement is false. The third statement, there exists a student S such that for all station Z, there exists an item I in Z such that S chose I. Well, that was a bit of a mouthful. Let's try and interpret this. So there is a student right? That was this. There is a student that chose an item from every station. So we have to see if there's a student who took at least one item from each of the 4 stations. All right, well, we'll start with Uda. Green salad, spaghetti, pie, milk. He chose a salad, main course, dessert, and beverage. We're done. Uda chose an item from every station. This is a true statement. By the way, look at Tim. Salad, salad, main dish, dessert, dessert, beverage, beverage. Tim also took an item from all 4 stations. Ewan, however, didn't. He didn't choose a salad, but it doesn't matter. We only need to find one. And so this is a true statement, because in fact, both Tim and Uda chose an item from all 4 stations. Finally, the fourth statement, for all students S and for all stations Z, there exists an item I in Z such that S chose I. So if we interpret this, every student chose an item from every station. Well, we've already proven this was false by looking at the previous statement. We said that Ewan did not choose a salad. And so that's a false statement. So we can use the rules that we discovered when we studied quantifiers to negative statements. Oh dear. Sorry. This should not be negative. This should be to negate statements with multiple quantifiers. And of course, that's going to block that. So to negate a for all x and d, there exists a y and e such that p, well, this becomes there exists an x and d, right? Because remember, negating a universal results in an existential. Such that for all y and e, because again, remember, when you negate an existential, it becomes a universal, not p. So there exists an x and d such that for all y and e, not p. So again, remember, when you're negating a statement, you're asking yourself, when would it be false? Well, it would be false in this case when there is an x such that for all y, your statement p is not true. Then to negate there exists an x and d such that for all y and e p, that becomes for all x and d, there exists a y and e such that not p. And now again, we're going to use a Tarski's world to look at this. So we have the statement for every square x, there is a circle y such that x and y have the same color. We wish to negate this and then determine which is true, the original statement or the negation. Now remember, one of them is going to have to be true. So the negation, I'm going to write it up top. For every square, there is a circle such that x and y are the same color. So the negation is there is a square x such that for every circle y, x and y do not have the same color. So let's look at the negation first. Is there a square that does not have the same colors every single circle. Well, what are the colors of the circles? We have gray and we have blue. Well, there is a square, black, E. So the negation is true. Same Tarski's world, but now we look at the statement. There is a triple X such that for every square Y, X is to the right of Y. So the negation, again, I'm going to write it up top. For every triangle X, there is a square Y such that X is not to the right of Y. So again, I'm going to look at the negation first. So for every triangle X, there is a square such that X is not to the right of Y. So is there a square that is not to the right of every triangle? Well, yes, E. E is to the left of F, D, and I. So the negation would be true. Dealing with multiple quantifiers takes practice. That concludes our study of multiple quantifiers.